I'll just say a few words. Okay. Hi everyone, we'll start a few minutes late because there's people still coming in who need to check their COVID certificates. So for the people here, just so you know, the microphone is this. You can just sound everywhere in the room. So when the lecture starts, if you're talking to your colleagues, it will probably... Okay, so maybe I can start, just say some words of welcome while people come in. So welcome everyone to the summer school on quantum thermodynamics. So this was organized mostly by me and Nuria Nurgalieva. They're on the back. We're both researchers on information theory. So this school was made possible due to our academic sponsors. So in first place, SwissMap, who is co-organizing this school. They are a network of mathematical physics in Switzerland. They own this research station where we are, so they arrange for accommodation of everyone that's here and your meals, etc. This was all paid by SwissMap. Them, and in particular, Elise Raphael, who's there at the end. She's been our contact point, and she's the local organizer. So if you have questions about the region, where to go climbing, best hikes, ask Elise today, because she's only here today. Then we have the sponsor from the Quantum Center of ETH Zurich. So this is a local network. So it's a center at ETH of all the groups working on some kind of quantum science technology. So from physicists like theory to experimentalists doing actually ion traps or superconducting qubits or this matter, to material scientists to computer scientists and so on. It's a fairly new center and we'll be organizing more events like this later. So they sponsored the trip of all the students who needed travel support, all the speakers, and also all the online apparatus. So all the getting our servers up and running and also getting internet support for people who are watching from countries where they needed like special mobile internet for this. Okay, good. And last but not least, Squid is the organization that Nuri and I founded. It's a non-profit and it's made just to organize summer schools like this. So we'll be having more, hopefully next summer in quantum foundations, maybe quantum computing next autumn. Okay, so this is all. I will now give it like 5 minutes or so for people to arrive and then we start. So if you're waiting at home, you can get a coffee. Nice. And see you soon. Our first speaker is Matteo Lostaglio from Amsterdam. No, it's complicated there. Okay, and you'll talk to us about quantum resource theories for thermodynamics.
Thank you, Lydia, for the introduction, and thank you to all of the organizers. I cannot say enough how happy I am to see students in person and friends and colleagues in the audience. It's really amazing and exciting. And but I would like also to double thank the organizers, because they organized this event in this hybrid format. So there are many people that cannot, for one reason or another, be here, but they still can join us throughout the world. So this makes this much more interesting. I'm going to talk about a resource theory approach to quantum thermodynamics. So this is an approach very much inspired by quantum information theory. And I would like to start with just maybe briefly contextualizing what this resource theory is in general and how it fits in this big box, which is quantum thermodynamics, which is this really umbrella term that includes so many different things that sometimes it's really difficult to actually know what's inside. There's just so much. But maybe some of you come from some fields that are related to what I'm going to talk about, but not quite the same. And it's nice to see how everything fits together, I think. Of course, as Lydia said, please interrupt me at any moment. So maybe let's see. So quantum thermodynamics, of course, it's a very old subject. It goes back to actually the origins of quantum mechanics itself. And one of the first somehow topics that people really thought about are quantum engines. This is one of the first questions that people ask. So we know and cherish not all of the study of engines in classical thermodynamics and how they work. And the question was, of course, what happens if I shrink the engine down to the scale of single atom, single molecule, when quantum effects cannot be neglected, and what happens to the standard relations, what happens to Carnot efficiency, what's the power of these machines, what would happen if we could build them, is there any advantage in doing so, and so on. So this is one topic that probably started the whole field, but there are many other directions that people took. One is the open quantum systems, open quantum systems. So this is a way to study, to somehow generalize the Schrödinger equation to situations where you want to study the interaction between a small system with a big environment, and you cannot or you don't want to actually describe the Schrödinger equation of the composite system and environment, because that would be crazy difficult, but you still want to give some dynamical description of what happens to the quantum system itself. And this is somehow giving you tools to actually do that. And of course, these two fields are talking to each other. Very often you're going to use these kind of tools to study this kind of systems. Of course, there is statistical mechanics, quantum statistical mechanics, that I guess we all encountered at some point in our studies, the study of phase transitions and the study of quantum statistics and what happens. Again, usually what happens when you got a large number of systems, which are quantum systems interacting with one another, and can we use statistical reasonings to say something about these systems? Yet another direction is the one of fluctuation theorems. So these are a set of results that are studying what happens when you take a system that is initially in equilibrium and you kick it out of equilibrium. No? And there are some things that we know already. For example, what's the amount of work that you need to change the Hamiltonian of a system from some initial to some final Hamiltonian. And we know that the minimal amount of work is going to be related to the free energy difference between the initial and the final equilibrium state. Okay. So, but these theorems are somehow much more refined versions of that statement. So they really ask the question of, what's the probability that I need a certain amount W of work, because this is going to be in general fluctuating quantity. And, if you've got a macroscopic systems and you can use the tools of statistical mechanics, then somehow the average, it's telling you everything about the system. But, when you got, you go to the micro scale, actually fluctuations are very relevant. And, you want to say much more than just what's the average amount of work. You want to say how this is fluctuating in every single instance of your, every single realization of your problem. Of course, this is all, again, interconnected. People use quantum fluctuation theorems while studying systems through open quantum system dynamics. So these are all meant to be somehow related to each other. And then there is more recently, quantum information also started to get into the picture, and it started to actually inform all of these different approaches. So people were studying, for example, generalization of statistical mechanics, where you cannot use these limits of these thermodynamic limits, when somehow the average is not informative enough. So people have been starting to think about what's called one-shot statistical mechanics, for example. But one important somehow way of thinking that quantum information brought to the picture is this resource theory approach. So this is what I'm gonna talk about today. I'm gonna I'll give you an initial introduction, then there will be other lectures that will put a lot more depth into the picture. Philippe, Renato, Nelly, Elena are gonna tell you much more about this. But with this kind of picture, I just wanted to say that there are many different approaches. They are useful in different contexts to solve different problems. So it's not that there is one approach that is better than the other, and it's good to try to relate one with another and see, can I use some of these in this context, because maybe there are some problems that are hard here and easy here, and vice versa. So kind of trying to exploit the strength of the different approaches to study problems. So the resource theory approach. Okay. So this kind of approach was actually born much earlier than people started to think, oh, we should apply to quantum thermodynamic problems. It's somehow it was already applied to many other fields within quantum information theory before, like maybe 10 years ago or something like that. People started to think, hey, we should also apply to quantum thermodynamics. So what's the general kind of mindset that informs this kind of approaches? People usually think very much in terms of tasks, limitations, and resources. Should be this, okay. So what does it mean? Okay, maybe I'll start with a very maybe silly example. Yesterday I had a task which was to just travel from Milan to here, and as many of you, I face a limitation, which is, I cannot go really by foot. It's limited, and then because of that limitation, I could identify certain resources, which in my case it was okay. There are trains that are helping me do this task because they help me overcome this limitation that I have. And of course, if there are no limitation, you can define a task, but if you don't define a limitation, there is no resource because you can do everything. So what is a resource in a world where you can do everything? So, so that's a kind of general way of thinking. And it was applied a lot in quantum. So one, maybe the oldest example is one where, for example, what I want to do is open some quantum communication channel with another agent. So for example, I want to send you a qubit. And maybe I'm facing a limitation that I can do any local operation in my own lab. So you are somewhere else again, maybe you're in Milan and we are here, and I want to send a qubit down there, but I can only do local operations in my lab, and I can call you on the phone, so I can do classical communication, and that's everything I can do. So I cannot send you the qubit for whatever reason. Maybe, if I send you the qubit, the channel is very noisy, gets degraded, so it's not good enough for what I want to do. And then because you face this limitation, then there are certain things that become a resource to you. And in this case, that resource is entanglement. In fact, it's famous somehow quantum teleportation protocol, where here I am. So this is Milan, and here I am, and I want to send this qubit here to Milan. And what I have is that in advance I share some entangled state with my friend in Milan, and here is my lab. And then if you do a certain measurement called the Bell measurement here, you communicate the result in Milan with your phone. Your friend in Milan is going to do a correction on this side, and at the end of the day, what happens is that you're going to have a qubit, the qubit in the same state that you had it here, it's going to be Milan. This is the quantum teleportation protocol. Which is what's basically happening is that even if I'm restricted to do only local operations and classical communication, because I had some entanglement share with the person down in Milan, I could suddenly actually perform a channel, which is just sending the qubit down to Milan, even though I didn't physically send the qubit down to Milan. I did something else that only involved entanglement and these operations. This is a resource because it allows me to go beyond this limitation. So another task where people thought a lot in terms of, in these kind of terms, is universal quantum computation. For example, one of the most common frameworks, the limitation is that there are only certain operations that you can do freely, meaning that, again, for certain reasons, for example, because your quantum computer is noisy, there are certain errors you can correct, others you cannot correct. And there is a certain subset of all possible quantum dynamics that you can realize, and a subset of all possible state preparations that you can realize. This is defining this subset of all possible computations, which is called stabilizer computation. So you prepare certain states that are called stabilizer states, you do certain dynamics that are called stabilizer dynamics. Doesn't matter now what they are. But then what happens is that these kind of things are actually classically simulatable. So they are not very useful to do actually universal quantum computation, meaning generic quantum computation. But then what happens is that once again, you have some resource. These are states, certain states that are called magic states. That's a fancy good idea to call them like that. And if you use these states, and even if you're restricted to do only this, computation, which is really only somehow classically simulatable, if you join these two things, you can actually do any computation, any quantum computation that you want. So again, these are states that allow you to overcome a limitation. So all of these different ideas, and people thought, well, can we use the same sort of ideas in a thermodynamic context? So we would like to define somehow a set of thermodynamic processes that in some sense I can do for free. And then there will be some limitation there. In this case, it's going to be that essentially, it's going to be a limitation that stems from the fact that there is a thermal environment around us, meaning that in general, things are in equilibrium, and then if I want to bring them out of equilibrium, I need to pay a cost to do that. And then we're going to see that there are certain resources also in this theory that are going to correspond in some sense to ordered energy, ordered in somehow opposition to the energy, which is the energy in a thermal environment that is very disordered with high entropy. This is going to be a energy with very low entropy. And actually, we're going to see that there is also a second resource in this kind of theory, which is coherence. Coherence, I mean superposition of different energy states. For example, this one here. And of course, this is something that we are used to also from classical considerations, where you want to talk about work, how much work do I need to do that, how much work can I extract from this process, and so on. Whereas this is something that comes into the picture because we are talking about quantum mechanics. So it doesn't have classical analog. Okay. So any question about this broad picture, or should I move on? So let's try to be a little bit more precise. So what is a resource theory? I'm thinking about these various examples and distilling out the kind of general structure. So every time what I'm doing in this context is I'm saying there is a set A of free or allowed operations. So this is a subset of all possible state preparations, all possible quantum dynamics, all possible measurements that you can do in quantum mechanics. So this defines a set of free operations. Attached to this set of free operations, there is a set of free states. So free states are states that you can prepare for free using these free operations, okay? For example, in this case of entanglement, it was actually states that are not entangled. You can show that you can prepare them using only these local operations and classical communication. But any state that is entangled, you cannot. So the free states there were the non-entangled states, and the resource states there are everything else. So resource states the non-free states. So whenever I define such a theory, what this theory defines is some sort of ordering on my set of quantum states. So what do I mean? I mean that I've got all my various quantum states. So the zero state, the one state, the plus state, the maximum entangled state, whatever, no? And then, there could be, I have now my set of free operations, and I'm asking the question, can I map this? If I give you this state, is there a free operation that transforms it in this other state? If yes, I can draw an arrow. If not, I'm not going to draw anything. And then I will get some sort of something like that, for example, some relation between these various states. No? And as you can see, there are certain states that are essentially equivalent, meaning that it really doesn't matter if I give you this one or this one, because you can interconvert one to the other and vice versa. So these are really equivalent as resources. There are certain states that are strictly better. So this state is strictly better than this other state. Why? Because, well, if you needed to do something with this state and I gave you this other one, you can first do the conversion to this other and then do whatever you wanted to do with this one. So this is strictly better than this one.
Our states with zero discord are considered as resource, yes?
Depends on the theory that which theory do you refer to? It depends on your set of allowed operations and
The state we can be prepared with LOCC are free.
yes, the states you mentioned can be prepared with LOCC. And then what's also important is that there are certain states that are actually incomparable. What does it mean incomparable? Well, I cannot go from this to this one, and I cannot even go from the second to the first. So these are totally incomparable states, totally incomparable resources. Okay. And if you think about it, what the second law tells you in the context of thermodynamics is that certain transformations are forbidden. Somehow it's telling you that certain arrows are not here, certain transformations cannot be done. And I'm going to leave you something to think about.
You raise the board.
Oh,
You
yes.
can swap them if you want. You can send the other one down.
Well, I need to write a bit more here.
Send it totally down to the floor.
Okay.
And the other one up a bit.
Okay, maybe, yeah, that's better. Yeah, thanks. So this is a claim you can think about in the next days, and actually will be solved in another course, is that if you have a single entropy, so a single either, okay. So either all states are comparable, or a single entropy is insufficient. So what I mean by that is that you're trying to capture this sort of ordering, and I'm saying that usually the way we do it is by introducing some entropy, yes, and then we're gonna say that if the entropy say it's decreasing, then there is no transformation mapping, in this case, for example, y to x, because transformation should increase entropy. But then if you think about this, either you have a situation where all of the states can be compared, meaning that you never have this sort of situation where you can not go from either the first to the second, nor from the second to the first. So either this doesn't happen, or if this does happen, then actually you immediately can start to see that introducing a single entropy, which is what we do all the time in classical thermodynamics or standard considerations, this is not enough to be able to capture, fully characterize this sort of ordering. This is not totally obvious, but I think Renato is going to talk a lot about this in the next day. So just left it here just for you to think about. Okay, this is everything I wanted to tell you about resource theories in general. And now I want to introduce the resource theory for thermodynamics more formally. So do you have any questions about kind of this general context?
Yes, in this example that you mentioned about entropy, here if you have a bipartite system, X is the state of the whole system, yes? Or the subsystem?
Yes, I'm imagining this is a state of the whole system.
The whole.
Yes.
It's not always an entropy. It could be the mutual information between
Yes.
things.
So this is, Yes, really, yes, thanks.
There's not a single function that fully characterizes this order. It's pre-ordered.
But, I was looking for a connection with second law of thermodynamics, which states that system can go from a state to another state if the entropy increases. It should never decrease. Okay, but here by S you don't mean entropy, yes?
We'll see that this is a necessary but not sufficient condition. So it doesn't capture everything.
Yeah. So, yeah, thanks, Lydia. So by entropy, like here I've been slightly vague. I just mean any functional on the set of quantum states. And what I mean is that you're mapping all of these complex, it's actually called a pre-order. So you're mapping this complicated ordering down to just a real line, essentially, if this is a functional on the real line. And this is not really enough to capture complexity of disordering whenever you got the situation that you got in comparable states. So in the thermodynamic context, we usually introduce entropy functions. And then, whenever we go out of equilibrium, this kind of incomparable states and this complicated ordering starts to appear. And you can start to imagine why we're going to get into a situation. And I think Nelly is going to tell you much more about this, where you need to introduce a lot of different entropies to capture this complex order.
Your notion of comparability, do we have disjoint graphs, or is it just necessary that 2 points cannot be directly joined by an operation?
This second. So I'm there, and then yeah.
So you say the single entropy is insufficient. So my question that I'm trying to understand is, how would that pop up? Like, so I get a set of states, I take my entropy, and now when you say two states are incomparable, what would entropy of these two states look like? Would they be equal? Would they be infinities? Or what would it be? What's the issue that we will see if I try to set up this theory?
Well, yeah, it's going to be a number, not the entropy. So either the entropy of this is bigger than the entropy of this, or the entropy of this is going to be bigger than that. Yeah, but it's going to be equal. But in any case, it's
yeah. But when it comes out to be they are incomparable, what would the entropies look like if two states are incomparable?
So comparability is just an operational fact. I'm just saying that you give me some set of free operations, and I cannot find any way to transform this into this, and I cannot find any way to transform this into that.
So it could be anything. It could be bigger, or it could be smaller, it could be the same.
Bigger, it could be smaller. And I'm giving you the freedom. Just choose your favorite functional that you are going to call entropy. And the point is that whenever you got this set of incomparable states, just giving me a number for each state, it's insufficient to capture the situation. Because you would like a situation where I just look at the entropy, and if the entropy is lower, I know I cannot go, and if the entropy is higher, I know I can go. This is somehow the situation in equilibrium thermodynamics. But then here we're going to talk about actually non-equilibrium thermodynamics. The situation is more complicated, and the basic structure that prevents you from just having the nice sort of single entropy that we define in kind of thermodynamic textbook is this incomparability here. But I don't expect that you fully understand this whole picture, because actually I mentioned it because Renato, I think, is going to talk about actually this thing in particular. So it was more like a small pill for you to think about before you actually see the course.
Yeah, sorry. I think you already answered the question I would like to ask. It's like I was thinking in the case that a single entropy is not sufficient, should I think the system in the language of thermodynamics, the system is not in a thermalized state? But I think you already answered, like I shouldn't think it as a thermalized state. Maybe I could ask, maybe you mentioned for the free operations, is there some like mathematical definition for what free means here?
Yeah, so it is actually In principle, it's whatever you want, meaning a subset of all possible preparations. You tell me which quantum states you are free to prepare. You tell me a subset of all allowed quantum dynamics. So this formally is represented usually by the set of completely positive trace for service maps, and you give me a subset of that, and then all possible measurements, so a subset of all. Even though usually there are certain extra properties that are satisfied, like closure under composition or convexity, these are typically satisfied because operationally it just makes sense. If I can do A and I can do B, I can do A and then B. Or if I can do A and B, I can toss a coin and decide if I'm going to do A or B. So there is some physics that enforces typically some structures, but in principle, this is up to you to decide. And it depends on what kind of situation you want to capture, what kind of limitation you want to capture.
So whether the states are comparable or not won't depend on your choice of the set of free operations.
Yeah, it will depend, even though basically most choices will be such that this kind of states emerge. Entanglement theory, all of the examples I showed you, actually there are this sort of states.
So just a very small question. So we always think about, okay, weak states operations are channels, or is this some abstract pre-order set?
Yeah, typically you think about it in terms of a subset of channels, but there are even more general situations that you may be interested in describing where your objects are not channels.
Okay.
Like the objects on which you're operating are not states and the channels themselves. Yeah, you can go really crazy with this. It's such a general structure.
So it's not a question, actually. I just want to clarify what we're talking about. So even in classical thermodynamics, you have incomparable states. So measuring the entropy doesn't tell you if one state can transform into the other. So let's say you have a gas and an egg. You can measure the entropy of both systems. So you'd think that a gas would have a higher entropy than the egg, because the egg is like a more ordered system. So you can measure the entropies of the two systems, but that doesn't tell you if you can transform one system to the other.
Yeah.
Because you know you can't transform the gas into an egg. So entropy doesn't give you information about transformations. You can always measure the entropy. You can always find a functional that will give you the entropy of a system, but that doesn't give you information about transformations. So even in classical thermodynamics, you have incomparable states. Well, the situation is far worse in quantum thermodynamics.
Okay, yeah, I guess then it's yeah, it is debatable, I guess, if there are or not incomparable.
Even in axiomatic thermodynamics, you have states that are incomparable. So it's not a feature of quantum thermodynamics. It's a feature of classical thermodynamics as well.
Okay, maybe let's talk about this during one of the breaks.
Yeah. So we leave clarifying questions for the lecture and comments for the breaks. Maybe one last question there, and then we move on, because it will become so much clearer once we see an actual example. No, after the break. Debate on the break.
So, okay, enough with the general stuff. Let's talk about the free operations in the standard approach that people use for the resource theory approach to thermodynamics. So the set of allowed operations are called thermal operations. What are they? So you can do a few things. You can draw a thermal state from the environment. What we are really measuring is that there is some environment and some temperature T out there. And we're going to define these operations with respect to this equilibrium environment that is surrounding us. So draw a thermal state from the environment. So this means taking a state of the form e to the minus Hamiltonian of the environment over KT divided by the partition function, which is just a trace of this guy. And then the Hamiltonian, of course, of the system is just HE. So here I just denoted state and Hamiltonian, okay? So you're allowed to take any such states where this guy is your choice. But the temperature is fixed, okay? All right, I can take this, I mean, imagining I'm surrounded by these states and ideally I can take any such states, I can prepare any such state. Second, I can do what's called an energy preserving unitary. So what does it mean? It means that I've got my, if I have a bunch of systems here, S1, S2, S3, each of them has its own Hamiltonian, HS1, HS2, HS3. I'm imagining that at the beginning they are separated and now I bring them together and make them interact through some unitary U. And the unitary U, it's gonna preserve total energy in this specific sense. It is commuting with the sum of this system Hamiltonian. So you're imagining that you're turning on some interaction. And this is generating this unitary, but at the end, you're again separating the system. So the Hamiltonian at the beginning and at the end is just given by the sum of these three Hamiltonians or any number. And this relation tells you that the unitary is preserving the overall energy of all of these systems.
Remote environment is also part of one of these tests, one of these.
Yeah, you could. So if I give you a system, already, you can start to combine these things. So I give you a system that you can take one of the states from the environment, and then you can couple the system with the environment. And then you can also do yet another thing, which is discard, let's say discard the environment, which in quantum mechanics, this is described by a partial trace. This is the operation that represents kind of, removing some state from your description. This is the partial trace. I think you're probably familiar with this. And it just means that, if I take one of these environment, I'm interacting with the system, then at the end of the day, I take my system away and I can forget about the environment, don't care what's the final state of it. So you can do all of these things. And of course, you can combine them. So there are different ways of combining them, but the way that we be using the most is the following. So you're going to give me a system. This is some out of equilibrium system. It's described by some density operator ρs. This is a system on which you want to act. And then I can draw some thermal state from the environment because I am allowed to do one. So now I'm just showing you, what I can do by composing these things. So I can take some thermal state from the environment with a general Hamiltonian HE. I can do a unitary on the joint. Okay, where the unitary is going to commute with the sum of the system and the environment Hamiltonian. And then I can kind of forget about the environment. I can do a trace over the environment. Okay, so this is going to define a channel on my system. So a channel, just a description of the dynamical evolution of the state, and what's the input and what's the output. So this is the trace. Okay, this sort of channel, it's called a thermal operation. when I talk about the allowed free operations in this theory, you should think about thermal operations. So why did we allow these operations here? Why not some other operations? So of course, what we are trying to capture here is operations that we can do without paying any sort of thermodynamic resource. No? So why not something else or something more? For example, why shouldn't I be allowed to take some, say, thermal state with some Hamiltonian HE and some different temperature? Or the question is, should I also be allowed to do that? And if not, why do you think?
Sorry, what was the question?
So I said that I can do this set of things. These are my allowed operations. This is a definition. No? So whenever we introduce a definition, we should think about what's the physics behind it and if the definition makes sense. So what I'm asking is why can't I do something else too? Why does it make sense to think of these as the set of free operations? So for example, the first thing is, I told you, you can draw a thermal state from the environment with arbitrary Hamiltonian HE, but I told you the temperature is fixed. So now I'm just asking, why did I tell you that? Why shouldn't I be allowed also to introduce some other state with different temperature?
Otherwise, you could create a mobile perpetual mobile, no? Because you can always take the system out of equilibrium, couple with the bath again, equilibrate, and in the equilibration process, you extract work, and then you repeat the process, so that you are always extracting work for free.
Mm-hmm. So I guess you're all familiar with the idea of a Carnot engine. So this is an engine that works by exploiting the fact that you have two environments, one at a colder temperature, one at a hotter temperature. So if I tell you that I'm free to not only draw states from an environment at temperature T, but also to draw states from another environment at temperature T prime, suddenly I have two environments at different temperatures. From these two environments, basically by running a Carnot engine, I can get work out. So in this theory, I would be able to get unlimited amount of work out of my free operations. Okay, maybe you're interested in such a theory, but such a theory wouldn't be a theory of thermodynamics. It would be a theory where you have unlimited amount of ordered energy at your disposal and you want to do something else with it. Okay, so that's why we don't allow environments with different temperatures. Okay. Similarly, you could ask why not unitaries, say, that don't commute with this. That's also a fair question to ask.
It's the same.
Because of the first law, you are not conserving energy.
But what could you do if I gave you such a unitary?
You could extract the energy from the unitary as well. Same problem.
Mm-hmm. So yes, you could extract indeed energy from the unitary. So one thing you could do is I give you such a unitary. I told you that I can draw this thermal state, and so I can apply my unitary on the thermal state. Okay, on the thermal state only, and this condition would tell me that if I had this condition, the unitary would need to commute with HE.
So we see it in the camera, but I don't know if the people in the back can see that look.
Sorry. Apologies. So, for example, what I could do, I could apply this unitary to this thermal state. Now, if this was an energy preserving unitary, this guy would commute through because the unitary needs to commute with the Hamiltonian. And so it would leave the Fermat state unchanged. So if it was energy preserving, this would be the effect. But if it's not energy preserving, then I can start with a Fermat state and make it not thermal just by applying one of these unitaries that are not energy preserving units. So now I've got not only my Fermat states, but also non-Fermat states. Now, it's not totally trivial that this is something you don't want, but as you can imagine, once you start to create things that are out of equilibrium, you can start to think, okay, now I can actually get some work out of these states because I can make them equilibrate back to equilibrium and get some work out. And this is in fact something you can do by generating lots and lots of these copies of these states. It's not totally obvious, but it's something you can do. So once again, we see that if we try to kind of weaken the number one, the assumption number one, we get infinite amount of workout. If we try to weaken assumption number two, the same happens. So this is the physical justification behind this set of operations here.
Good time for a break.
It is a good time for a break. Let me just finish with one sentence, which is following. So the resource theory that we're going to study is one where the set of allowed operations is the set of Fermat operations. So the set of all channels that I can obtain by composing these transformations, which are going to be taken to be this set here, and the set of free states, at least if I'm interested in just what happens to the system, it's just going to be the Fermat state of the system. This is something I can prepare on the system just by, you give me whatever state you want, I throw it away, and then I just throw from the environment a state with this Hamiltonian. This is something I can do. So, but there is no other state with this Hamiltonian. No other state with this Hamiltonian that I can realize. Okay. And then the kind of central question of the theory is what transformations are possible and what transformations are not possible. So we want to know, given any rho and sigma, say, two quantum states, does it exist a channel C of that form, thermal operation, such that when I apply to rho, it gives me sigma. So, and this is in some sense this ordering that I was mentioning. So I can go from rho to sigma if that happens. Okay, let's have a break.
Yeah, there's one question.
Yes.
Just a naive question. So, this question could be strange, but then what if we relax the condition that there is no interaction between S and E? Can we put the interaction inside? Is anyone considering this kind of structure?
So you start with a situation where system and environment are coupled.
Okay.
That's what you're saying.
I was thinking like whether there's any possibility that you actually allow the total Hamiltonian to be HS plus HE plus H interaction. And because, roughly I remember someone did something like they considered the initial state of that evolution to be non-product. But I forgot about the detail, how they consider this, because there may be this well-defined problem of your local input. I just wonder whether by doing so, you can have some Gibbs preserving channel that is not the operation, just an idea.
Okay. So I don't know for sure,
yeah.
But so first let me say, so this is HS, but of course S can have many constituents. Yeah. So there can be interactions between the constituents. So what's really discriminating between system and environment is that the environment, I can actually isolate my system. So that's why I'm calling it my thermodynamic system and I'm not calling it my environment. There are situations that people are interested in where there are interactions between system and environment, and for some reason these interactions are always there. And this is a problem for every kind of thermodynamic approach, not only the resource theory, but also in open quantum system dynamics and others. And then it becomes a bit conceptual and a bit technical in the sense that then why are you calling something a system if it's always all the time interacting with this environment? I cannot really tell the two apart. There are some ways, there are some techniques called reaction coordinates where people try to kind of bring in a piece of the environment into the system and say, okay, now this extended system is something that is only interacting very weakly with the rest. So this is now my system. And then you can go back to this kind of assumption on an extended system. Or, the system Hamiltonian may be something which is not just the system Hamiltonian, like the bare Hamiltonian, it may be normalized by this coupling with the environment. So there are many subtleties that are there, surely. In some sense, you want to call system something that you can isolate and you can kind of interact with independently of the environment, at least in this approach.
I mean, there are couples, right? I mean, the unitary couples.
Yeah, you
they
can.
are interacting.
You can indeed couple. So if you think about what happens here, now think about this in time, because here we're using, as we're doing a quantum information kind of mindset where everything is discrete and just apply this unitary. But now if you think about what's actually happening, that I'm turning on some interaction Hamiltonian. So at some intermediate time, the situation would be very much the one you discussed. But then the question is what happens at the end? At the end here, I'm imagining that the interaction is switched off again, so that the system is again the thing that I call system before. But if the interaction stays on, then it's more complicated and you should do the sort of things I was mentioning. Maybe you should redefine what your environment is. You should now trace not over, but maybe you bring in a little piece of the environment and you just trace over the rest. And okay, this is more kind of advanced.
Okay. Sorry, what?
Sorry, we can go.
Okay. Just one more question is like, so we know that the Gibbs preserving channel is like strictly bigger than this system operation.
So what is calling Gibbs preserving is any channel
that Gibbs thermostat to thermostat.
is any channel that satisfies the
And I just wonder, like, is there any Gibbs preserving channel like these that will have the problem that you mentioned? Just like this unlimited amounts of inspector work.
No, it's more about creating coherences where you shouldn't.
Yeah,
Okay.
I don't think so.
Okay.
So, but we'll get into these details in tomorrow's lectures, I think. Also, Philip Feist is the expert here and is in the room, so you can.
He knows everything.
Yeah, I know.
We have a, let's say, 10-minute break and we start again at 10:15. Okay. There's no coffee. The coffee comes after the next lecture. Everyone, we restarted.
Okay, cool. All right, so last thing we said, we define our resource theory, allowed operations of thermal operations, and three states on given system S is just one because the state of that system. There is no other three states with this Hamiltonian. Basic question: is there such a transformation mapping is initial state to this final state? So you can think about this as some sort of out of equilibrium generalizations of questions that we usually ask in equilibrium thermodynamics. So can I go, from the gas with this pressure, volume, temperature to this other pressure, volume, temperature by adding this much work, for example? Here we are asking this question at the level of quantum states and at the level of, in general, these are out of equilibrium, of course. Neither this one or that one is an equilibrium state. Okay, so maybe before we proceed further, it's good to think about some examples of thermal operations just to get a little bit more intuition about what they are. So let's start with probably the most trivial example of all. Consider channel C that when you apply to a quantum state rho, it's just giving you the thermal state. So it's just totally thermalizing any state that you put in input. So is this a thermal operation? And if yes, how do you realize this operation? By the kind of steps that I mentioned? Yes, well.
Yes, and you can just like switch and the unitary is just put the mutation of the two systems.
Exactly. So what you could do is I have my system, rho s, and then I bring in environment, which is just the thermal state. And then I do a swap unitary, which is allowed because the Hamiltonian of both systems are the same.
Wait, can you be to be like the camera is looking all over the place? Give me a second.
And then you can just, if you want, you trace away.
It's just looking at this.
Sorry, what was that? Somewhere.
Yeah. We started assuming that the Hamiltonian of the environment and the system are the same, right?
No, we didn't assume it. We just use our freedom to draw any thermal state from the environment with fixed temperature, inverse temperature beta, and arbitrary Hamiltonian. So in particular, I can choose it to be exactly the same. I can swap, and then I just trace away the second system. And this defines a channel on the system, which is exactly this channel.
But we have to fix the Hamiltonian, as well as we fix the temperature, we also have to fix the Hamiltonian at the beginning of.
You can take any environment Hamiltonian that you want, and you can then do any energy preserving unitary, of course, energy preserving with respect to the Hamiltonians that you chose for So the environment.
And following that, I can change my Hamiltonian and do another operation.
Following that, sorry.
Following doing this operation, I could combo it with another one with a different Hamiltonian.
So if here you add a different Hamiltonian, can you now do the swap?
No, I'm just asking like, we had to fix the temperature when we started, but do we also have to fix the Hamiltonian?
You fix, so when you fix the results theory, you fix beta. And then that's it. Now I'm just telling you, I'm giving you this system, ρS with this Hamiltonian HS, what can you do to it? And then you tell me, well, one thing I can surely do is to do this operation, which just formalizes that system to its own Fermat state. I think you were simultaneous, at least.
Yeah, how exactly do you draw out this thermostat of the environment?
How? In what sense? How experimentally do it?
I mean, I would find it somewhat more intuitive if it was the real environment Hamiltonian somehow. I don't know.
You can, so this is the kind of general setting where we try to allow a very general set of operations. You can be more restrictive if you want. You could add extra conditions on, oh, maybe for some reason I can only draw systems Hamiltonians that have that particular structure. Then you define a subset. That's your own now resource theory that you can study, where the environment Hamiltonians can only be, I don't know, single mode bosonic paths, I don't know. And then you can study that theory if you want. So surely you can impose more restrictions here. This is just a general setting where one does not impose any restrictions. So in principle, you can bring any environment Hamiltonian as you want. Of course, in practice, that would be extremely difficult, I mean, impossible to do. Yes.
Questions?
Is the Hamiltonian of the free state fixed, or is it just any Hamiltonian? Because you can, it seems you can anyway initialize any state from.
Yes, so the Hamiltonian of the system for now it's fixed. I'm going to tell you towards the end how you can deal with situations where you actually want to change the Hamiltonian of the system. It's not supernatural. You need to do a bit more work to do that.
Fixed, you mean during the channel, right?
I'm
fixed in the sense that I can only pick one Hamiltonian in the beginning of the.
I mean that at the beginning and at the end, the
unitary swap
Hamiltonian is just HS plus H. In the middle, there is a lot of interaction, so. Okay. All right. So let's see a slightly less trivial example. So we have our quantum system, and then we imagine that there is a large environment, large bath, at temperature T, and these two are weakly interacting. So people have been studying kind of extensively this kind of setting. And in the case where, let's be even simpler, this is a single qubit. Actually, this sort of interaction induces a very simple set of channels, which are of the following form, say as a function of now I'm giving you this channel. So this is really a family of channels.
Matteo, can you just repeat very, very quickly, last minute?
Last minute.
Because now the camera is working.
Okay, so I was just giving a few examples of thermal operations just to get a bit more idea of what this big box contains. The first one that we discussed is just a very simple one, is one where it's a channel that takes any state and maps it just to the Fermat state. And we saw that this is indeed a thermal operation. One way to do it is just by drawing an environment with Hamiltonian, which is the same as the Hamiltonian of the system, and then you just swap the two and you trace away the second system. If you check what this does, it does exactly what we want, it maps any state of the system to the Fermat state. Then we started to see a slightly less trivial example where you have, for example, a single qubit quickly interacting with a large environment. And typically what you get by this sort of models is an interaction of this, dynamical evolution of this kind in time where there is a constant gamma and where you have an exponential.
The opposite.
It's the other way around. You have an exponential thermalization to the, well, exponential thermalization, exponential approach to the Fermat state as a function. So again, is this a thermal operation?
You can do a rotation which is not a full swap, but an incomplete rotation between the two.
Partial swap here. Yes. Partial swap, I think, would, you mean to realize this?
Yes, then it is correlated.
I think this, yeah, I think this would do the job. Yeah.
A conditional swap. Conditional swap, not partial swap.
Condition swap. Condition on.
I have to introduce an ancillary system as well.
Yes. Okay. I think maybe both things will work. The second, this one will work. So if you think about it, what this is also just a convex combination of two operations that we know are thermal operations, because this is, if you want, is 1 minus P, the channel that we just introduced, the channel that maps every system to the Fermat state, plus the probability P. So this is, if you want, is 1 minus P let me call it T, the channel that thermalizes every state, plus P, just the identity channel on OS. So these are clearly both thermal operations. So if you know that thermal operations are a convex set, so you can do a mixture of them, then you know that this is also a thermal operation. Indeed, you can use an approach like the one that was suggested to prove that these thermal operations are convex. You need to introduce some ancillas. Actually, this is something you find in the exercise sheet. Okay. So this is also free thermal operations. Yes.
This is really the question, but what is the difference between operations and channels? Are they the same?
Yeah, in this context, it is the same. Quantum operation is more general than a channel, but in this setting, it is. Sorry, I'm gonna use one or the other. And okay, so these are two examples of thermal operations. And let's see another one, which is a bit different. So this is. Let me start here. Okay, so this is one where again you have a system, and now what you're gonna do, you're gonna actually put it, for example, in a cavity. So you put an atom in a cavity, and this cavity we imagine it's just supporting a single mode of the electromagnetic field, and the atom and the single mode they are interacting. There is an Hamiltonian, which is the James Cummings Hamiltonian that you may be familiar with, which is describing this sort of interaction. Okay, so this is this is the annihilation operator. This is just creating an excitation on the qubit. And this is removing an excitation from the qubit. And this is the creation operator. So basically what's happening is that either you're creating a photon and removing the excitation from the atom, or you are doing the opposite, and these two things happen coherently. And then, okay, so this is the somehow the interaction of Hamiltonian. So this U is I'm gonna have a unitary which is of this form, and now I can take my bosonic. The Hamiltonian of the system is whatever, and the Hamiltonian of the environment is just going to be the number operator. Now I can compose everything and obtain a Fermat operation. No? I can do an operation on the system, which is just I'm tracing the environment, and do unitary, which is the James Cummings unitary on system, and so the bosonic path, single mode bosonic path prepared in a Fermat state, and then I trace away the environment. Okay, this is from operation. You just need to check that this is commuting with the Hamiltonian system plus the environment, and this is, you can check, it's not very difficult to check. So then this is defining a Fermat operation. I guess one interesting difference between this example and the other example, I don't know if you did a little bit of open quantum system evolution, but this is what's called a Markovian evolution, which essentially means that this channel can be split in many, you can think about this channel as the composition of many distinct channels applied one after the other for a very small time, delta t. So this is a channel of this kind that can be divided in this way, whereas this channel is something that involves some non-Markovian effects, which basically means that there is continuous exchange of information between the system and the buff. And the physical reason for this difference is that here it's something that it's an interaction between an atom and some large buff. So, there is some memory about, the fact that these two interacted, but this memory is kind of lost inside this very large environment. Whereas here, the environment is just a single mode. There is no place where this information can go. And so it's kind of constantly going back and forward in the system and environment. In fact, after a period, you go back to some initial state, if you kept evolving under this unitary, unless there is some leak or some noise or something else. Okay, so these were some examples of Fermat operations. Any questions about this? Okay, so now, we define general, the general context, then define Fermat operations more specifically as a resource theory. We saw what sort of maps are inside, like complete thermalizations, partial thermalizations, which model interaction with large buff, but even situations that are not under the typical of thermodynamics, like in this case, the environment is very small, just a single mode, and this is still a Fermat operation. So it includes things that sometimes are described by what's called master equations, if you ever saw these kind of things, and things that are not described in this kind of language. So small, big environments, all of this is included. So now the question that you may ask is, okay, there are so many different things inside this set. So what are the sort of core properties of these Fermat operations? What are properties that are shared by all of them? One core property of thermal operations is that, let me call it maybe T, that stands for thermal fixed point, is that if you apply a thermal operation C to a thermal environment, nothing is happening. Okay. And this sort of makes sense because a thermal environment is something which is a zero resource state, it's something I can create for free. And any other state is not something I can create for free because it's out of equilibrium. So if I apply a free operation on a free state, I shouldn't be able to get anything which is not free, no? So something in this case which is out of equilibrium. And indeed this happens. So these properties are also in the exercise sheet for you to check. And this is somehow, again, realization of, if you want the second law of thermodynamics, you cannot realize, you cannot take a thermal environment out of equilibrium without spending any resource. You need some work to bring it out of equilibrium. Okay, this is quite intuitive, but then there is another property of these operations, which is a symmetry condition, which is less obvious, which is the following. So I have my system, so I have an Hamiltonian on the system, and I can define a unitary, which is just the free evolution. Let me call it V, maybe. This is just the free evolution of the system. So if I have my system, do nothing to it, don't couple the environment, it's going to evolve under its own free Hamiltonian, bare Hamiltonian. So this is what's going to happen. So let me call V then. Just, okay, this is acting on density operators in this way. So this is just the evolution under this Hamiltonian of the quantum state OS. So what's this symmetry condition is that if you give me a thermal operation C, okay, and so this thermal operation is encoding my interaction with the environment essentially. So if you do this interaction with the environment and then you let the system evolve freely for some amount T, this is going to bring you to the same state as if you did the opposite, meaning that you took your state, rho s, you let it evolve under your its own free Hamiltonian, and after some time t, you couple it to the environment. Okay, so like here you're doing free evolution and then coupling system environment. And in the second case, you're doing the opposite. Time zero, you're coupling it with the environment, and then you're letting it evolve for some amount of time t. These two things are the same. This is called sometimes covariance or time translation symmetry. And it's an important property because then it allows us to use symmetry reasoning to say various things about what can happen in these thermodynamic processes. Maybe one other property of these operations is that they can never generate coherence. So if I give you a thermal operation on the system, no, and I do just nothing on some ancilla, okay? And I start with a state rho SA, which is incoherent. Then the final state, so let me call this final state rho SA, sigma SA, then sigma SA is also incoherent. Let me remind you what coherent means. It means state is coherent if it has some superposition of different energy states, and it is incoherent if not. Or more formally, if you have some system rho with some Hamiltonian H, rho is incoherent only if rho commutes with its Hamiltonian. If it's stationary under free evolution, it's called incoherent. So this is telling you, this is a kind of coherence non-generation condition. It tells you if you start with something that is incoherent and you apply your thermal operation, it stays incoherent. You cannot just generate coherence under these operations, which also kind of makes sense because you're basically interacting your system with the thermal environment. The thermal environment is an incoherent mixture of different energies. And so, and crucially, the unitary is energy preserving. And if you put these two things together, you get that you can never create any coherence. You cannot go, say, from, even if you're lowering the energy, say, you cannot go from the state 1 to the state just a plus state, equal superposition of 0 and 1. Okay. I will leave you with a question, which is also in the exercise. Are these two equivalent? So coherence, non-generation, the symmetry condition, are they equivalent or not? So this symmetry and coherence non-generation, are they equivalent?
And in this case, then Scylla is also preparing an incoherent state, or okay.
The whole raw SA is incoherent, and then the output is incoherent.
Snap with the Scylla is
This is just the identity. So,
just the identity map.
so this is an extra freedom. If you want, you can also extend your, you can input some state on your system and just do nothing on some ancillary system. And maybe the state is entangled between system and Scylla. That's allowed. So if the input is coherent, the output. So this is coherence non-generation. And yes, I will leave you with this question here.
So maybe this is a good point to.
We should stop here. Okay.
So we stop with this question. Coffee break is half an hour, so we restart at 11:15. You need to wear a mask to get to the coffee break, and there you don't need a mask. Matteo, you good to go?
Okay, guys. I'm already late. What I wanted to say, but that's okay. So we saw the four properties of thermal operations. Thermal state is a fixed point, and coherence cannot be generated, which is related to the symmetry condition, which is time translation symmetry. Remember that a state rho x with some Hamiltonian hx, so a system in state rho x with Hamiltonian hx is said to be incoherent if and only if it commutes with its Hamiltonian. So what I mean here by coherent, I mean coherent in the energy basis. So superpositions of different energy states. Okay. Okay, so to kind of start to be able to say something a bit more quantitative about this theory, there is an important concept which is the one of monotones. This is a concept which is common to all resource theory, and in a resource theory, remember that you have a set of free operations, and a monotone is functional on the set of quantum states. Quantum states takes quantum states and splits numbers, reals. And a monotone is something such that for every allowed operation, if you compute this quantity on some state rho, this is going to be bigger or equal than if you compute the same quantity on your the state after you apply your free operation. So these are quantities that never decrease under free operations. Of course, you can also define it the other way around. You can define it as the ones that never increase. But yeah, never increase or never decrease. But okay, for now I'm gonna define it. Define that in this way. Okay. There is a very important monotone in the theory of thermal operations, which is the non-equilibrium free energy. So this is a monotone that is defined as follows. So the non-equilibrium free energy of a quantum state is going to be minus kT log of the partition function. So this is, if you recall your thermal studies, this is just the standard, the equilibrium free energy, plus there is some non-equilibrium component. It's the relative entropy between this state and the corresponding thermal state, which I'm going to call tau. Okay. Just e to a minus beta hs. What is this relative entropy? Relative entropy between states, it's defined as follows: minus log y. So this is sort of measuring the distance between these two states, even though this is actually not symmetric, so it's not appropriate to call it a distance. But when rho is equal to tau, this is 0. So you see that if I feed to this guy equilibrium state, this is going to be 0, and I just get the equilibrium contribution. And if I feed to it a non-equilibrium state, I'm going to have the equilibrium plus the non-equilibrium contribution. So this is called relative entropy. Okay, I wanted to show you a nice decomposition of this quantity, which is the following. So if you take this relative entropy between the system and the thermal state, you can actually additively decompose it as two contributions. One is just the relative entropy between the system and the diagonal part of the system. So here you have a quantum state rho. You write it as a matrix in the energy basis. It's gonna have its diagonal components, which are going to tell you the probability of occupying different energy levels. And you have off diagonal elements, which are telling you about the coherence between different energies. Yes?
Sorry, this definition of free energy, what is the intuition or physical reasoning behind it?
Yes. So actually, there is a whole exercise about this, about the non-equilibrium free energy. Why are we kind of, from now, as you said, I just defined it out of the blue. I gave you a little bit of intuition, which is somehow adding a non-equilibrium contribution, but then you can prove that it has many properties that are analog to the ones you expected from equilibrium thermodynamics.
So equilibrium classical thermodynamics.
Yes. Like that the maximum amount of work is bounded by the change in the free energy. And
problem here, in classical thermodynamics, for example, you have a system at temperature TA interacting with the system with a bath at T bath temperature TB.
No, wait, I stopped you there. Here we are talking about a rheospheric fixed temperature. So this is analog of isothermal processes in the kind of classical setting.
So the system and the bath are equilibrium. The temperature of both systems are the same, you mean?
But the system is out of equilibrium. It's not, it doesn't even have a Gibbs form. It's whatever you want. And the environment is at some temperature T. And the reason why it's the free energy and not the entropy or not some generalized potential that is relevant here is exactly because I'm focusing on this class of operations, but then you could try to extend and look at more general transformations too. Using particle numbers or other stuff. So you got your density matrix, and then you can decompose it as, of course, just this part plus the small, yes, the off diagonal part. Okay, which is what I'm calling rho 0 plus, well, everything else x. No? So what I'm saying here is that this relative entropy can be decomposed as somehow the distance to the thermal state can be, you can think about it in two steps. First, the distance between the state and its kind of classical version, the one where you remove all of the off diagonal elements from the density matrix in the energy basis, plus another component, which is just the distance between now this diagonal part and the thermal part. So this part measures how far are your occupations of different energy levels from being thermal. This part measures how far is your quantum state from being incoherent, meaning just having only this diagonal part. So if you have a plus state, okay, the density matrix is this one, and you're just decomposing it as identity plus for example. Okay, so this would be rho 0, this would be the rest. Okay, so you have this decomposition here, and then if you kind of plug it here, what you discover is that the free energy of a state rho can be split into the free energy just of the diagonal part plus KT, well, this quantity is called sometimes asymmetry, which, as I said, is quantifying the coherent content of your state. It's the relative entropy between the state and its diagonal version. So now you can think about this as you have a classical part of the free energy, which is just the free energy of the diagonal part, plus a quantum part of the free energy, which is just the contribution that comes from the off-diagonal superposition of different energy levels. Okay. And what's interesting about this decomposition is that F is a monotone, but also FC and FQ separately. What do I mean? I mean that if you do a thermal operation, maybe I should do a thermal operation, now you go from some state rho to some state sigma by means of a thermal operation. Here I can draw FC and FQ, okay? These are lines of constant total free energy. Because F is the sum of FC and FQ. And it's not only that if I start with rho, I can only reach states with less total free energy. So this is the condition that F of rho is bigger or equal than F of sigma. This is true, you can prove this condition, but actually separately, the classical part must be bigger or equal, and the quantum part must be bigger or equal. So here basically means that actually it's more like that. I can only go here, or at least these areas are excluded because both of them needs to decrease. So the rule of the games here is you define monotones, you try to prove that they are, always say decreasing under your set of free operations, in this case, thermal operations, and this gives you constraints on what can happen. So these are somehow, in some sense, generalized second laws out of equilibrium. And Nelly is going to talk a lot about this, how you introduce many of these quantities. Okay. Any questions about this? Yes.
Sorry, can you give a physical intuition for FC and Q?
So, the classical free energy is so if you take your system and you completely dephase it in the energy basis, meaning that you remove all of the quantum part in some sense, you make it just an incoherent mixture of different energies, what remains is the classical part of the free energy. The quantum part of this free energy is all of the components that are actually due to the superposition. So, I mean, in general, a state is out of equilibrium, both because it's all stationary, it's not a mixture of energy levels, and because even if I only look at the occupations or the probabilities, occupations of different energy levels, these are not Gibbs distributed. So now here you see that you can actually additively, for this measure, split it into one contribution plus the other, which is a special property of this quantity.
Right, thank you very much. The initial you are basis dependents, right?
Yes.
Okay, so basically the monotones which are basis dependent. So monotones basis.
No, they are more.
To be in the energy basis.
No, energy. Of course, energy is fundamental in thermodynamics. So the whole of thermodynamics, in some sense, is basis dependent, and these quantities are defined according to some basis. Yes, which is the energy basis of the system.
We consider rho and sigma. It is can it extend? It is for asymptotic, no? Asymptotically.
It's any transformation. I'm saying that if there exists a thermal operation, so these are some unnecessary conditions. If there exists a thermal operation map belonging to sigma, all of these things must happen. So if I give you a sigma, say that is here, now you compute its quantum free energy, you check that it's bigger than the initial one, and you tell me there is no thermal operation. Now, of course, these are useful because how would you do it otherwise? You would need to run over all possible choices of the environment, all possible choices of the unitary. This is unfeasible. So these monotones help you to do that. And similarly, if you find it here, you say, oh, now the total free energy is decreasing, but the quantum part is increasing. This is also impossible under thermal operation. So these are all constraints that needs to be satisfied if a transformation is possible.
My question was, these conditions are applicable for standard size.
They are applicable for every rho and sigma. No other conditions on it. You can apply to many. You can apply it in particular to this if you wish, and this. You can do that.
In classical thermodynamics, when we're going to the we derive inequalities of free energy or the second law of thermodynamics just because of some ambiguity about the microscopic position or moment of the particles. Okay, but when we go to the microscopic picture, we have full control over the system. I mean, for example, when you say I have a U, the unitary means you know which state you want your whole system. Now I don't understand where does these inequalities come from physically. What I understand in classical thermodynamics it comes from this ambiguity about the microscopic position, but in quantum microscopic thermodynamics, physically I don't understand it. Why do I expect these inequalities to appear?
Well, this is just telling you basically that if you've got a quantum system interacting with a thermal environment, then if you had at the beginning some probability of occupation of different energy levels, this is going to get more, that occupations are gonna look more thermal as time progresses, just because the interaction with the thermal environment is making the ordered energy that was there at the beginning in the system more disordered because of the because you're interacting with a thermal bath. Whereas this one is telling you that the thermal bath being incoherent environment, it's going to degrade the amount of coherence in your system. So you're gonna get entangled to this environment, and then once you look at the system only, this results in a damping of your coherence terms, which is what happens, all the time when we build quantum systems, and then there is always this environment that is, degrading our coherent properties and going to eventually make the system completely incoherent in the energy basis. And this is a more quantitative kind of version of that statement.
Because this, I don't want to take too much time. Okay.
Good thought.
Very good.
Let's move on. Comments at the end.
Okay. How long do we have still? Like,
You have half an hour.
okay. So let's see what can be fit. Okay, so I wanted to show you a couple of applications. Okay, so for now we don't have many tools because everything we've got is these monotones here, and Nelly is going to introduce many more kind of technical tools to be able to answer these kind of questions. But we can start to see, start to kind of gain a few insights, even with these kind of limited tools, about what transformations are possible and what are not, and what this tells us about somehow the difference between classical equilibrium thermodynamics and quantum non-equilibrium thermodynamics. So, applications. So the first thing I wanted to tell you is that we are often interested in certain protocols, which, you know, in which we are doing certain processes that are very common in thermodynamics. One of them is to try to get work out of a quantum system. So, for example, I have a quantum state rho, no? And then I imagine that I'm going to introduce a battery state that is initially in its ground state. Okay? And then what I would like to do by means of some thermal operation is to get some work out of the system. So in particular, imagine that this battery system is just a qubit, no, with a gap W. And what I would like to do is to just excite this system from the ground to the excited state. So essentially, I would like to extract a form of ordered energy, because as you see, if I manage to just excite it, I'm gonna end up with a qubit which is in an excited state, and it's also in a zero entropy state. So this is a very ordered form of energy. So I'm going to some sigma tensor 1. So here the Hamiltonian of the system is HS, and the Hamiltonian of this battery is basically just this one. Just very, very kind of simple model of a battery, just a single qubit. So there is this phenomenon that is basically that we cannot actually, in this kind of setting, we cannot get any work out of the coherent component of the system. Okay? So the maximum amount of work, no? So I'm gonna try to maximize what's the W that I can get in this transition, no? So I would like to make this the biggest. Let me call W max the biggest that is possible. So the biggest such that there exists indeed this thermal operation mapping one into the other. So the maximum that I can achieve, and I don't care about what's the final state sigma, it can be whatever I want. It can be thermal, it can be anything else. The maximum amount of work that you can get from a quantum system rho is actually bounded by the maximum amount of work that you can get from just the diagonal part of rho. This may be a little bit surprising in the sense that we just said that the free energy of the non-equilibrium free energy is actually the one attached to the diagonal part of rho plus the one attached to the off diagonal part of rho. So there is some amount of free energy that is in the off diagonal elements of the state, and that cannot be actually extracted in this kind of setting by means of thermal operations. And this is actually a consequence of the symmetry condition. So the symmetry properties that we saw. And you can obtain it easily by noticing that if you think about the operation of dephasing, so the operation that takes any state and puts to zero all of the off-diagonal elements, this can actually be written as an average of this kind. This is the operation, the dephasing operation. So essentially, if you take a state rho, it's gonna give you a state sigma such that all rho ij are put to zero. Okay, this is not exactly true, but it's almost true. So no, I mean basically, imagine now that the Hamiltonian is non-degenerate. So there may be some I and j that corresponds to indices with the same energy, and that wouldn't be true. So this is only killing all of the off-diagonal terms in the diagonal in the energy basis, meaning all of the terms corresponding to different energies. Okay. It puts to zero it puts to zero That's the point. It puts to zero all of the terms corresponding to different energies, okay? In first approximation, just puts to zero all of the off-diagonal terms. So if you apply these dephasing operations on both sides of this transformation, you see that this dephasing actually contains this average over the free evolution. And because of the symmetry condition, actually the dephasing commutes with the thermal operation. So because as we said before, this is satisfied for every thermal operation, and we just said that the dephasing operation is just an average over all of these unitaries, then you can show that this is true. And this follows almost immediately. But here we said, assume that there exists a thermal operation that is mapping, which is extracting an amount of work W. So here there was a thermal operation doing this. Okay. Now I apply dephasing on both sides. Now on this side, I can commute it through by exchanging according to this relation. This goes inside and I get the following. So this is incoherent because it's just the ground state is an incoherent mixture of energies. It's just the zero energy. So I just get dephasing of rho tensor 0 equals to dephasing of sigma tensor 1. Okay, so basically what I showed you is that if I can extract some amount of work W from the state rho, I can extract the same amount of work W from the state D of rho, so the D-phase version of rho. Okay.
So why is it smaller or equal or just equal?
Why it is smaller or equal? I guess another point. Because smaller or equal is also equal. No, yes. So the maximum is the maximum that you can get from the D-phase version. Okay. So there is this amount of free energy which is in the quantum part that cannot be extracted. So a note. So this doesn't mean that you know, this is absolutely unreachable. It means I need some extra resource to get the coherences out, let's say, to get the coherent contribution out as work. Okay, this would bring us to this whole idea of introducing these extra states that are themselves coherent superpositions that I'm using as an auxiliary state to do these kind of transformations, but this would bring us kind of a bit far. Yeah, this is the basic idea that work, so the work in coherence is locked. As a kind of locked in a sense. And you need something else. You need some extra ingredient to unlock it, okay? This is of course a phenomenon that really only appears in this quantum thermodynamics context because there is no analog in classical of superposition, okay? So this was one thing. And the second,
But the dephasing operation is the dephasing is also a term operation, right?
Yes.
Okay.
Yeah, it's
I'm not sure if I understand, because why I'm choosing the phasing here, because of course, if the phasing operation is a term operation and you are choosing it to apply first, you kill the off-diagonal elements.
Yes.
Couldn't you choose any other, let's say, operation in which you don't kill and you prove that that work in coherence is wrong? In other words, why we chose the coherence operation and not the coherence, but the phasing operation in this case?
So what I showed you is that if rho tensor 0, goes to sigma tensor 1 by some thermal operation, then the same thermal operation actually, bless you, actually maps this into. So then this means that whatever I can do with the full state in terms of, I'm actually interested in maximizing this, the W here. Okay, maybe I can write it like that so that it's clearer. This is some state with energy W. I want to maximize it. So just find what's the transformation and maximize this W. Okay, found it. This is going to be a thermal state, doesn't matter, it's going to be something. But then I tell you, look, whatever that operation is, I could actually get the same W from D of rho just by first dephasing and then just doing the same operation. But then this means that the W that you found actually cannot be bigger than the classical free energy of this, because you see, I can actually just get the same W from the dephase version. So it means that I'm actually losing all of the quantum part of the free energy. So if you want, you can apply. So you found here your W max, whatever that is. But then I know that this actually also happens. And then just by using again that the free energy is a monotone, what I get here is that the free energy of the dephase state, which is the classical free energy of rho, is bigger or equal than the classical free energy of sigma plus W max. The best that I can do is actually to take these guys to be thermal, so that essentially this contribution drops, and I get that the maximum work is bounded by the classical part of the system. Questions? Okay, a couple of last things. Something which I think it's also pretty obvious, but it's kind of cool to state, is that work is not universal. Usually we're in classical thermodynamics, we're used to the idea that, if you pump enough work into a system, you can do whatever transformation you want. You can trivialize any of the constraints, say the free energy constraint can be trivialized. So if you pump enough work, you can do whatever you want. But here, this is not the case. And the simplest example to see that this is not the case is to take an initial state that is incoherent, tensor W, so pure state with energy W. And then I'm telling you, can you do a thermal operation and map it to some state that is coherent by consuming some amount of work W? And I'm not telling you, you can take as much work as you want. And again, the question is, can you actually do this or not? And don't have enough time to make you think a lot about this, but the answer is no.
Give you 10 minutes more.
Okay, I'm almost.
So you have 20 minutes now.
Okay. So the answer is no, and again, it's a consequence of this symmetry condition. Can anyone see why then? Even we have a few minutes more. So I'm saying, basically, I'm asking about what sort of states can I achieve by applying a thermal operation on some sort of state, a state like that.
The overall coherence is increased.
The entropy, no, well, the entropy, it depends, no? This could be very entropic, but with a little bit of coherence.
This is diagonal, so
The ones, well,
I will say that evolution is not time translation covariance. So in this, you cannot find a time translation covariant map such that you can do this, no?
Yes, you cannot create coherence to incoherence.
Yes.
yes. So I think someone else also said it,
So the coherent contribution of the free energy, as you said, FQ of rho, is increases in the process.
Yes. So this is, for example, one way to just compute the quantum free energy, the quantum part of the free energy, and you know that the quantum part of the free energy on the left-hand side is zero because this is completely incoherent, and this quantum part was only quantifying the contribution from the coherent part, whereas this is non-zero. So this would be a situation where a monotone is increasing, and this is impossible because this is something you can prove in general, that these thermal operations never increase the free energy. So
I have an answer on YouTube.
oh yes.
So someone said, well, didn't you say at the beginning that if you start with an incoherent state, we end up with an incoherent state?
Yes.
By everything in classical, what do you mean? Because in classical, we don't have coherence. No. So you can compare this.
Well, I'm saying that this is exactly the difference, that somehow one should think in terms of two different resources, one with a classical analog and another one without a classical analog. And it could be the case, and in some frameworks, it might be the case that this resource with a classical analog can be freely interconverted in this other quantum resource. But in this case, this is not the case. You have two different resources, and you know, they are not interconvertible in one another, because you cannot, independently of how much classical free energy you have, because here you have an unbounded amount of classical free energy, but I'm not giving you the quantum part of the free energy, and so you cannot do this transition.
Yeah. You said before this from the symmetry argument, how do you just said monotones. How do you derive this one?
Yeah, the symmetry argument would be, let's say, let's prove that the final state is stationary. If I show you that the final state is stationary, it means it's incoherent. And I'm gonna check if I apply the free evolution, is it going to change or not? And you know that because of symmetry, you can exchange those two. And now this is the free evolution of the incoherent state. So this is doing nothing. So now you just prove that the state C, this final state, is stationary. And the only thing you really use is the symmetry.
And how do you define work? What's your definition of work?
So you can, okay, there are different models you could use. Here I use kind of the simplest model, where what I'm trying to do is that I allow you basically to take a two-level system in with a gap W in an excited state. This is this W here, and you can make the gap as big as you want, but you can in fact take essentially whatever diagonal state you would like to pick. You can pick it if you want, and it's still gonna be impossible to do this.
I mean, it's Robert Alinsky's definition of work. I mean, rho H dot, yes.
So H, sorry.
Rho D, you know, trace rho D H is Because these two systems are interacting, yes?
So here I'm doing a thermal operation on a system and a battery. So I have my system, yes. Then I have my battery, and I gave you the freedom to choose, the battery with, an excited state as big as you want, or you could even choose something else, as long as it's diagonal, it's fine. And then this is being interacted by a thermal operation with a thermal environment. And what you're trying to do is, basically this is a system, this is a weight in a sense. And then you also have at your disposal a thermal environment, and I'm telling you, do whatever, do whatever unitary, energy preserving unitary that you want, coupling, system, battery, environment, use up as much work as you want. I would like you to make the state, which is initially incoherent, into a coherent state. Can you do it or not? And here we argue that independently of how big this weight is, you can never actually, independently of how much ordered energy you have, you cannot actually transform it into a coherent superposition. This is a separate resource that should be.
Normal interaction Hamiltonian for the W and rho, yes?
There is no W and
S and W.
and S. No, these are two separate systems. I have my weight and then I have my system. So then I can turn on an interaction that involves everything at once. And then at the end, I'm going to switch it off.
Would we be able to get a coherent state if we were dealing with select units? Would there always
Yeah, so this is then getting into more complicated. It depends very much on what you allow me to do with ancilla qubit. Should it be given back unchanged? Should it be given back close to what it was at the beginning? Because if you start to allow other things, which you could, then you need also to tell me what are the rules of the game, because otherwise I could just take the ancilla, the state I want to prepare, and I swap it, and then I'm done. But then you don't want to allow it like that. You would like to put more constraints to make the game less trivial. But yeah, you can also go that road. So Lydia told me I had to talk about IID limit. So now, even though this is actually, I think it's actually quite complicated, and I wonder, the details are actually really fine printing. So the IID limit is something that people in quantum information often study, which is we always consider questions such as, can I map this state rho into this state sigma? And now I'm going to ask you, okay, can I map some state, n copies of some state rho into n copies of some state sigma? And I'm interested in particular in the ratio between m and n. So what's the best ratio that I can achieve? Okay. So it's the best ratio that I can achieve. And what I'm gonna do is actually, I'm gonna send n to infinity. I'm gonna send m to infinity. And then actually, I'm gonna be even more tricky. I'm gonna add a small error here, epsilon, meaning that actually, there is something called the trace distance, which is a measure of the difference between two states. And I'm asking that I don't want to get exactly sigma. I just want to get something that is very close to sigma. So I would like this to be smaller than epsilon, where this is the trace norm. Okay, this is just the definition, but doesn't matter. It's just a measure of the distance. I'm asking that these are essentially indistinguishable under any measurement, modulo some error that scales like epsilon. I'm adding an error, but I'm also making it going to zero. So as the number of copies are increasing, I'm being more and more picky about the error that I allow. So I'm making this number of copies larger, larger, and larger. This is some sort of thermodynamic limit, in a sense. where this transformation becomes closer and closer to the ideal only when I make the number of copies bigger and bigger. So this is called IID limit, and I'm typically interested in this, the best ratio that I can achieve. How many copies M can I get out of, per copy of? Yes.
Does epsilon have to go to 0 fast enough so that this that the error of these M copies of sigma epsilon to sigma to the M also goes to 0 as M goes to infinity?
Yes, so here I actually haven't told you exactly how to do the limit, and there are different ways of doing the limit, like different scalings you could choose for epsilon, and actually it turns out that this scalings is not irrelevant, that the way you make epsilon scale with the other quantities may, change the result. Philippe knows everything about this, I think. But yeah, so this needs to scale fast enough. It needs to go to 0 fast enough, otherwise. I guess.
As long as epsilon, you just want to make sure that there's still enough epsilon left, whatever you can have. So as long as it's slow enough to 0, you can even. So where is your terms? Okay.
So would epsilon be like scale something 1 over M, so that we have the error for the composed system that doesn't grow with M?
Let's chat about it.
Okay, yeah.
Yeah, I think
it's a good
you do want some scalings, because I think there are some weird embezzling phenomenon if you don't make things scale. Anyway, it gets quite technical, but basically the general idea is that you want this error to go, say in this sense, just to go to 0 only when the number of copies goes to infinity.
Sorry, question.
Yes.
I don't know if I got them. What's the deal with this transformation? What's the deal with this transformation? I mean, I'm transforming rho into sigma, but exactly why and why?
So instead of just asking, so before I was kind of asking, I want to get a single copy of sigma out of a single copy of rho. Now I'm playing a slightly different game. I'm saying I have actually a lot of copies of rho, and I would like to get as many copies as possible of some final state sigma, but I'm allowed to use all these copies at once. I don't need to operate on each copy individually, as I was doing before, in a sense. Now I can use them all together and try to kind of distill them out into some number of copies of this state sigma. And this is just the epsilon is kind of just technicality. If you allow some small error, and perhaps this error is just scaling in a way that it becomes 0 only when this number of copies goes to infinity. So this is something you're used to do very much also in entanglement theory, where you ask what happens when, not just when, can I transform this entangled state into this other entangled state, but you start to ask questions such as, if I have many copies of this entangled state, can I, how many copies of, say, the maximally entangled state can I get? No, and you ask this question asymptotically when n goes to infinity, because then you get very simple relations in the limit. But of course, the use is limited by the fact that you're taking this asymptotic IID limit.
And here it would be like, yeah, with a single shot thing, I can get just a small amount of work out of this transformation, and I can use several rows to have just like the maximum amount of work in a single sigma.
Yeah.
Something just in the.
Yeah, you would expect then many of the conditions that are necessary for the single shot maybe become irrelevant when you go to this asymptotic limit. And in fact, actually for thermodynamics is even more complicated than that, because you're really, because of this symmetry condition, there is always this underlying symmetry condition that is never actually going away, so that whatever you actually do, like in terms of the number of copies, if the initial state is incoherent, the final state is never going to be coherent. And then, okay, but then you can kind of go around it by allowing, basically you're gonna allow some extra state here, and you're gonna allow to consume this state. But this state is a superposition of different energy levels. So say from H equals 0 to some R, okay? And then you're telling me, okay, but then you're cheating because you're allowing some extra resource here. But then what people do is say, okay, but actually this R is going to scale, say, as some sublinearly with n. Okay, it's like, say, n to the 2/3. So when n becomes super large, like I'm adding only a number of copies that is the number of copies, the number of states that are superposed per number of copy of the state, it becomes very small. So basically you're kind of adding a very small extra coherence seed into this picture. If you do all of that, there is this paper by Fernando Brandao and others where they show that the maximum ratio between n and m is going to be just the free energy of rho, this free energy that we defined before, divided by the free energy of sigma. So basically, to tell me if this transformation is possible or not, you only need to check this single quantity, the free energy, and all others that you could have defined kind of collapse to this single one. They become irrelevant. So there is this huge simplification in this kind of limit that you may think in some sort of analogy with the thermodynamic limit, where you go from microscopic to somehow macroscopic, many non-interacting systems, and you kind of recover a relation that you were used to. I don't say classical thermodynamics because this is still a non-equilibrium free energy, but you were used to the idea that there was a single quantifier that would tell you if you can do the transformation or not, and you recover that in this asymptotic. But you see that there are many different ingredients and it's quite subtle. So yeah, so it's a very subtle limit to go to.
Okay, rho and sigma, can rho and sigma be incompatible?
Like here, I'm basically telling you that if you go to this asymptotic limit, there are no states that are incompatible. They become all compatible if you take enough copies.
And also using catalyst, consider kind of resource.
So the question was if I use a catalyst. So a catalyst is some extra system that you're putting in, and then you're asking me to give back to you uncorrelated and unchanged.
Yeah.
And in this limit, nothing is changing. You can do it without catalyst, with catalyst.
So catalyst is not considered resource.
In this setting, even if you allow me a catalyst or not, is inconsequential to the result.
What do you mean?
I mean that you get this result if you give me a catalyst, and you get the same result if you don't give me a catalyst.
So in the single shot, it matters.
Yes.
But if you have many copies, it kind of washes over this.
Yes. So if you ask me, can I go from rho to sigma, single copy, then I'm gonna ask you, do you allow me this extra catalyst or not? Because it's gonna matter. Whereas if you tell me, can I go in this asymptotic limit from rho to sigma, meaning many copies to many copies, I don't even need to ask you if you allow me a catalyst or not, because it doesn't matter. This is always the maximum ratio that you can achieve, and you cannot achieve a bigger ratio.
Even if the dimension of the catalyst also scales with it.
I think as long as the catalyst is given back exactly unchanged, it doesn't matter. If you allow then the catalyst to also be a little changed, then you can get all sorts of crazy things, because you have a very large system that you're changing just a little bit, but just by changing it a little bit, you could say you could get a lot of energy out of it just by changing it by a tiny amount, no? And then you can get it also. So you need to be very careful on what you allow.
Is the ratio of free energies or difference between free energy and it's the relative entropy to the thermal state, right?
Yes.
Yeah, I think for the way I defined it before, actually, the free energy difference between rho and tau. So it's
So Matteo, until this part, we were talking about always single shot scenarios. And then I understand that these scenarios motivate when you go outside the scenario. But do we learn something about the one-shot scenario by looking at this limit, or it's something experimentally motivated in another way, for example?
Well, I guess there is a little bit of intuition. Okay, I'm not sure how much you learn from this, back to the single shot. You kind of learn that there are many of these quantities that Nelly is going to introduce that are generalization of this free energy. They kind of all converge to this one in this asymptotic limit. So that's how, this is one other way of seeing how this ordering among states, this kind of graph that I was drawing at the beginning, kind of becomes simpler and simpler if you go to this limit. In terms of physics, I guess it tells you maybe something about thermodynamic limit, where you have many copies of very weakly interacting states and what happens there. But then it is still quite a formal limit in a sense. Maybe Philippe will say something more.
Nelly for sure will say something more. Right? I think Nelly will say something.
And Nelly will say, no, meaning about maybe IID, but yeah, and Nelly will say a lot more about the many measures that you can introduce beyond this free energy. Okay. Yes, so I didn't tell you about changing Hamiltonians, but maybe I'm gonna skip that. But basically, there was also a question at some point by some of you about how do I include the scenario where my system Hamiltonian changes from beginning to end because it was fixed. And in this kind of resource theory scenario, it's a bit more complicated than usual, in the sense that what you really need to do is to kind of introduce some clock system, which is kind of telling you, okay, this is the time 0, and then I'm going to some state at some final time that I'm gonna call 1. And I'm gonna say that the Hamiltonian is actually something like the Hamiltonian of the system at time 0, tensor 0, 0, plus the Hamiltonian of the system at time 1, tensor 1, 1. And then through this trick, say, for example, if I compute the average energy of this system, because of this particular tensor structure, the average energy at the beginning actually just gonna pick up the system Hamiltonian at time 0. And if I compute the average energy at the end, it's gonna pick up the system Hamiltonian at time 1. So you can kind of include Hamiltonians that are changing through this trick. And if you do that and you look at work extraction, you're gonna get this relation here of we're gonna get that if you go between two equilibrium state, the maximum amount of work that you can get out of the system is actually bounded by the difference between the equilibrium free energy at the beginning and at the end. I hope I got it the right sign. Basically, that's also showing you how you can go all the way from this very quantum and non-equilibrium scenario, go back to this equilibrium scenario, something that you're more familiar with from textbooks.
Work locking would still be valid.
Well, here actually I'm imagining, so here, okay, I didn't write it. What I'm imagining is that you just start from an equilibrium state with respect to this Hamiltonian to an equilibrium state with respect to the final Hamiltonian. So there is never any coherence around.
So yeah, we need to go for lunch, otherwise the hotel will kill us. But this is just the beginning of the school, right? So all the questions you have now, all the other lectures will get into this. Yes. Also, Matteo will be here for the full duration of the school, and he can answer your questions. So let's thank Matteo very much for his lecture. Thanks to everyone who's watching from home, and we'll see you again in the afternoon. Bye.